Hey, LJ Wilson here. I wanted to take a moment to talk about our little Wheel of Fortune simulation game from yesterday. I thought it was a really powerful learning tool. I think it wasn't really super well explained why things were related or why things were important. So I kind of wanted to go over it again. And if you like what I have to say, cool. And if you don't, well, you can skip the video. All right. So um, let's just get right to it. The reason why the Wheel of Fortune simulation didn't hit home with how powerful and important it was is because the first thing you did is you set the min and max winnings. In a world where you set the min and max winnings, the game is already over because you know everything there is to know about the results. But what if you didn't know the min and max values? How does that change your understanding of this experiment? So let's play a game. Oops, sorry. Let me delete this. Let's say that I wanted to know the average salary at my company. And so I said, well, let's start with what I know. I know my salary. And I'm breaking everything. Sorry, just clicking around here. Okay, so I'll take what I know. I know my salary. My salary right now is 31,000. I am using a rand function, so this number, of course, is going to change. So then I say, well, you know what? It's not enough to just know my salary. I'm going to ask my best mate. They make significantly less than me because they're newer to the company. And he asks his mate, and his mate happens to be a manager, makes a little bit more. Okay. So we poll 3 people and arrive at the conclusion that the average salary at our organization is 36,000. That number is obviously wrong. As we poll more people, we'll get a better picture of what average salary is. But let's take a moment and talk about the problem with average. The problem with average is that it's skewed by outliers. So I've polled my first 9 people, and they're all kind of anywhere from the new intern all the way up to the mid-level account manager. So I take the mean of those 9 people and I get 35,000. I'm like, yeah, I got a pretty good feeling about what average is at my company. And then I poll like somehow the senior director and one of the owners of the company, I don't know, and they tell me, yeah, their salaries are 100,000 and 250,000, and that skews my mean significantly. It almost doubles my mean, actually. And then they are like, oh, yeah, let's take this number and put it on glassdoor.com because that's our average salary of employees at our organization. Aren't we so great? Ha ha ha. Right? That's the problem with mean. Mean is skewed by outliers. Those of you who are working in data mining in R, this is why we have to deal with outliers in our data set because it will significantly skew our results. So we have other measures for analyzing or looking at our data. We, of course, have the mode function. The mode comes from the German or the French fashion industry. Fashion, mode. What's popular? Get it? Mode. What is the most common number? 36,000. Median says what is the midpoint in my data. That's used for calculating the interquartile range. Fine. Okay. So you take all of your data and you're like, you know what? I really would love to know what this looks like on a histogram. So you open up stat tools, you make a histogram, but you're like, I don't actually know what a histogram is. What is a bin? A bin is a bucket. A bin is a range of values. In this case, I'm saying, well, my first range is going to be everything between 0 and 30,000. And from then onwards, all of my bins will increment by 20,000. Okay. So I create these buckets and I count the number of observances in each bucket. I count the distribution from my original data set. So who's making less than 30,000? Well, that's me and the intern. And so that's where that number 2 comes from. What about 6? 6 is 30,000 through 50,000. Hey, that includes my mean or my mode, my most popular value, and that actually makes sense why this has the largest spike. Now I have a right tail goes out to the right, or a left skewed histogram. It is not normal. Looks like a Poisson distribution. I don't know. It's not normal. But why do we even care so much about normal distributions? We care about normal distributions because if this graph was a proper bell curve, then if you gave me two pieces of information, the mean and the standard deviation, I would be able to know everything there is to know about my data. Let's assume for a second that my distribution is normal, which it is not, but let's assume that it is, which is an assumption that we often make, but is often incorrect, by the way. Okay, so I have a normal distribution. I have the mean, 36,000, and then I have the standard deviation, 66,000. Now, what does that tell me? If I follow the empirical rule, it means that all of your data plus or minus from the mean plus or minus one standard deviation, so minus 6,000 through one positive 127,000, that's one standard deviation away from the mean, it should encompass 68% of my data. 68% of my data points, 68% of my salaries are in this range. And if I go within two standard deviations, that tells me, well, 95% of my salaries fall within this range. It just so happens that it's true. 95% of my salaries fall within this range. I guess that means my distribution's normal. I'm being sarcastic. It does not. You have such a huge standard deviation because there is so much variance, because the data points are so far apart when you include that outlier. I'm just going to put this up here for you to look at real quickly. There is a difference between standard deviation sample, standard deviation population. Sample divided by n minus 1, population divided by n. Why is that important? In standard deviation sample, you do n minus 1 so that your denominator is smaller, which means you, if the top represents error, you divide it by a smaller number, so your error is larger. If error is larger, that means you give yourself more space. So if I run standard deviation sample here, I say my standard deviation is 66.9. If I run standard deviation population, I'm assuming that I know all of the data points, all of the company average. Sorry. If I run standard deviation sample, I say, okay, I took the sampling and this is what I think the standard deviation of that sample is. If I run standard deviation population, I'm saying, oh, I know all of the salaries. And here's the standard deviation of all the salaries. There's a 95% difference between these numbers. Standard deviation sample is larger, which allows for more error because I don't know all of the salaries. That's my Cliff Notes version of what the difference between standard deviation sample and standard deviation population is. N minus 1 versus n. Okay. Take all this, put it on the back burner for now. Let's return to our Wheel of Fortune game. What if you didn't know the min and max? What if you didn't know that the most money you could win was 10,000, the most money or the least money you could win was 100? What if you didn't know that information? And I said, well, your data is normal. Or your sampling, you've taken, okay, so you don't know the parameters, but you've taken your sample of like 50,000, you've run the game 50,000 times, you have 50,000 samples, and you're like, well, in these 50,000 samples, the mean was 500, and that is actually the case. If you go back to your data, the mean of all of your samples was in fact 500, and the standard deviation was 220. You're like, okay, so I have this information. Now what do I know? Well, if you calculate two standard deviations away from the mean, you get 500 minus 220 times 2 is 60, and 500 plus 220 times 2, so that's two standard deviations, is 940. You can say, okay, I'm sure that 95% of my values fall within this range. And that statement is true. How far away are we from 0 and 10,000 or 1,000? We're actually pretty damn close. Sorry, I have the wrong numbers here. No, this is right. The most you can win is 1,000. So given that these numbers are correct, I actually have an idea of what the min-max was. The min-max was 0 and 1,000, or 0 and 10,000, whatever. Maybe I have the zeros in the wrong place. But my point is by knowing standard deviation, by knowing mean, and having taken a large enough sample size, we can approximate the parameters of the game without actually knowing the parameters of the game. Which takes us back to our salary game. In my salary game, I took a sample of 3 people. As I take my sample up to 1,000, or in this case 8, I get a picture of what average salary at my organization is. But I can't do it alone. So I enlist my manager, and I say, manager, I'm really trying to conduct this experiment to understand how good we are at, I don't know, distributing salaries equally amongst all the employees, like that would ever happen. But my manager then runs the experiment, and they come back to me with their results, and I'm like, dude, your average is so different from mine. Huh, how interesting. And then he talks to his manager and says, dude, can you run your experiment, run this experiment where you collect samples of people's salaries? And my manager's manager gets a really different number in terms of mean. So what happened? Well, because I'm new to the organization, I have access to people, I have bias, I have access to a certain salary range of people that are interested in answering my question. But isn't it interesting that how close 19,000 is to the actual mean? Huh. Okay. Then my boss, he's kind of that mid-level manager guy. He asks other mid-level salaried people-ish what their salaries are. And then his boss's boss asks people up in the boardroom. Go figure. Right? And that's why we have such skew, or such wildly different sample means. But this actually speaks to one of the things that were talked about earlier in the session yesterday, which was, how do you take a sample? There's a couple, in real life, there are a couple ways you could take a sample. You could randomly, just blind random, do a number generator, and that number generator corresponds to a cubicle number, and go to that cubicle, ask that person their salary. So you could take a random sample. Yeah. Totally random. Or you could do a systematic sample. The systematic sample was that, okay, you have a population of X, you're going to divide it into N buckets, and then you're going to sample the third person in each bucket. I could, for example, stand at the door to my building and ask every 5th person who walks through the door what their salary is. That would be a systematic way of taking a sample. Alternatively, I could do a stratified sampling. And that's actually what I did here. By asking people to take a sample who are from different strata, I'm, this salary range, my boss is in that salary range, my boss's boss is in that salary range. Everybody took salaries in different strata, or took samples from different strata, and that's why my results are so weird. And that is a valid method. Arguably, it would be more valid if we weren't taking salaries. So if I didn't stratify along salaries and then take salary measurements, like obviously that's air quotes wrong. Maybe it would be more realistic to say what kind of car you drive. That's kind of tied to your salary as well, but you get the idea. Okay, let's wrap it all up with a bow. To wrap it all up with a bow, this Wheel of Fortune simulation, by pulling many, many outcomes, we said, okay, in this one sampling, what were your average winnings? And that's, great, you take one sample. But what if you take many, many samples? Sorry, you conduct many, many experiments. Maybe you conduct the experiment on January 1st, and then 1 year later, 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 and maybe your parameters change. Maybe it's not always 0 to 100. At the end of the day, what ruined the game for us is we knew these parameters. But hopefully now you understand a little bit better why we care so much about normal distributions in terms of using the mean and standard deviation and the empirical rule to understand the range that my data can come in. I literally heard somebody say, I don't know what standard deviation is for, so that's kind of what inspired this video. Anyway, if you liked it, great. If you don't like it, or if I said something that's patently untrue, talk to Daniel. Daniel apparently knows stats really well, and he volunteered to answer all your questions. I'll catch you guys later. Bye.